Let me start by thanking everybody for being here. It's beyond humbling to be speaking to you about this. Things like this don't happen to people like me. Let's start with that. And so when I got the call from the foundation, I was just enormously shocked, but humbled in the best way. But as was mentioned earlier, so for all of the people who've worked, with me for the last 42 years, it's your fault, right? For having done all of this great work. In terms of the title here, what could I possibly tell you that you don't already know? An academic and life adventure. I should also tell the world that I'm still on time to embarrass you for having hired me. So with that in mind, what's today's main objective? Make absolutely positively no mistake that today's objective is to keep you from falling asleep. Because if you fall asleep, we don't communicate, and then I think you would rather be outside, even though it's not exactly the best day there. And in addition, let's make it a little lighter here, by having a little bit of fun here. And so what I'll try to do is give you a little bit of an overview of the type of work that we have done in terms of batteries and fuel cells, but also I've been here 42 years, and I don't spend every living moment here. There's other things, and so try to complement that by covering other things as well. So the roadmap here, a little bit of an introduction, this motivation for operando, and I will define what I mean by that. Then some examples, fuel cells and electrocatalysts, lithium-sulfur batteries, metal deposition, and then a little bit of pontificating here in terms of future directions, the Abruña Energy Initiative, and bear with me for a few minutes at the end, okay? And so the idea is to provide that sort of landscape, if you will. So if we look at energy storage, right? If you want to integrate renewables, you have to store the energy somehow, right? And nothing is better than electrical. Why? Because it's fungible, you can move it through the grid. It's high quality energy, meaning low entropy. And you can stop right there. That's all you need, right? And so you have typically the sun, wind, tidal. It's interesting that in 1900, there were more electric cars than internal combustion engine cars. That's a fact. We did not follow that track, but we would be in a different place if we had done that. And so when you look at these applications, they put great demands in these technologies. And so I basically summarize this whimsically saying, infinite energy, infinite power, lasts forever and costs nothing. And those are sort of the design criteria that we're trying to address. And so we're looking at having high energy and power densities, parts rates, long cycle reliability, and safety, as we see later on. We have gone a long ways from the early ones. And so here's a plug for a company that's in my last, Factorial Energy. They had a demonstration with a real car, no simulations, going from Germany to Denmark, 750 miles on a single charge, and they still had 150 miles in the battery. That's an astonishing accomplishment. And that's today. How about battery? Fuel cells. The first thing, fuel cells are not energy sources. As far as I know, there's never been a mine of fuel cells anywhere, right? So then why are they interested in fuel cells? A fuel cell is a device that efficiently converts the energy in a field to electricity, right? Especially when you compare it to the internal combustion engine, so-called heat engine, the so-called Carnot cycle. Anybody remember what Carnot's first name was? Sadi, because he was a sadist, that's right. Making us suffer through adiabatic expansions and exothermal compressions, right? And so if heat engine does work by having heat transfer from a high temperature reservoir to a low temperature reservoir. And the efficiency is given by T hot minus T cold over T hot in Kelvin. You have a car? Do you have a car? What temperature is the car run? 600, very good. So 600 minus 300 room temperature, that's 300 divided by 600. Even I can do that math, right? 0.5. That's a theoretical efficiency of your car. Actual retail value, 20 to 25%, meaning 75 to 80% of the energy content in your fuel is going to something other than getting you from here to downtown or Syracuse or Rochester. 80% wasted. Think about that. A fuel cell, on the other hand, can be much more efficient, 70, 80, even 90%. So even if you really screw it up and only get half of that, that's still twice what you get in a car. And that's the why. Okay. And here's a rendition that, say, some presidents could understand. So hydrogen gets oxidized, the electrons go through the external circuit to whatever device you have. Ions move across the membrane, and that basically completes the circuit. In a real life, it's a little bit more complex. The heart of the fuel cell is so-called MEA, for membrane electrode assembly. That basically is like a club sandwich with catalyst, layers, etc. So what do I mean by ex situ to in operando? Ex situ, I use a sort of fishing analogy here, right? You put fish on a line, that's clearly ex situ. You can put them in a bowl, and that's in situ. But if you want to see how Nemo lives, you have to get into the ocean, right? And so here is this is from the Atlanta Aquarium. So here you have Nemos, floating around. So what do I mean by this? These are very reactive interfaces. You cannot pretend, even though I'm sure most of you at some point in a typical paper, the cell was disassembled and rapidly transferred to a spectrometer. How many of you have written that? Fess up. A lot of us, yes. Unless fast is a few microseconds, you're dead. Because those things are operating very far away from equilibrium. And the moment you take that away, it relaxes. And so developing operando methods, it might be experimentally a bit more complex, but you achieve a level of understanding that you cannot otherwise. You make very few assumptions, and that's why we do this. So here we go, right? None of this, super that. So how many of you have suffered through my electrochemistry course and have the scars to prove it? Okay, for the rest of you, so you can take, a 3-minute break. I'll teach you enough electrochemistry to follow this up, okay? So as Milan was mentioning, electrochemistry by definition is an interfacial science. Everything is the surface. And you can distinguish bulk, let's say a couple hundred microns away from the surface, where things don't care and don't know that there's an electrode. As you get closer in, then instead of being ox bulk, it's an ox surface, meaning it senses the electrode. It can be then in intimate contact with the surface, and we put ox prime. Because of Frank Condon, there can be no more nuclear coordinates in the time frame of the electron transfer. So you go from ox prime to red prime, electron transfer took place, it dissolves, and then goes into the ball. So you have the coupling of mass transfer. You have to bring stuff in and out of that interface. Electron transfer, which is often what we're interested in. And then couple chemical reactions before or after the electron transfer, and of course, surface reactions. And then two equations, an Nernst equation that relates the potential to the so-called standard potential and the ratio of activities of both species. I mentioned activities we almost never know. So what do? We lie like everybody else. Assume activity coefficient is equals 1, so activity equals concentration. And you dispense with that. And then the Butler formula, which is probably the most important equation in electrokinetics that relates the current that you measure in terms of an exchange current, meaning the current when there's no net driving force. And so you get typical shapes like this. So this cathodic, anodic, and the net. Notice that when there's no overpotential, zero driving force, the net is 0, but you have equal and opposite exchange currents. And then rotating disk, where you hydrodynamically bring stuff to the electrode surface, and the current should scale as a square root of the rate of rotation. And then everybody's favorite, the ducts, from cyclic voltammetry. A little bit more on Butler-Fulmer. If this is the potential at which a process should take place, but it has a barrier, then you have to provide an overpotential, which is really a tax, or let's say the current lingo. Let's not go there. To get the reaction to go at reasonable rates, you can compare that to a different process, and to reach the same current, you need a higher overpotential, telling you that the pink here is a slower process inherently than the purple, the blue. In terms of batteries, batteries operate differently. So in most electrochemistry, we control the potential. In a battery, we control the current, which is basically controlling the rate. And so the expression here, the sign equation, tells you how that behaves. And they typically look something like this. And so you might, I'm sure, when you're having your fifth beer, why do those things look like that, right? So if we change them around, what does that look like? Please say a titration curve, right? Which they do. And what's the math behind that? Every freshman chemistry student knows Henderson-Hasselbalch, right? It describes that. And the equivalent thing here would be basically the Nernst. Mathematically identical, and that's what they look like. Okay, so you can wake up those who took the course before. So a little bit of stamp collecting here. We'll talk a little bit about order inner metallics, manganese cobalt spinels, testing a completely, and I mean completely person metal-free fuel cell, ECS, electron microscopy with STM, and here I should call out David Moller, who really, we could not do any of this without him. There he is, okay? And then X-rays here, and Joel, the same thing applies there in terms of providing with the guidance to do these experiments, lithium metal deposition, and a little bit about the so-called Abruña Energy Initiative. And so, as I mentioned earlier, the oxygen reduction reaction, it's got collective coordination into electrochemistry. Why? Because it's very hard to catalyze. You're asking a catalyst to develop or deliver 4 protons and 4 electrons in the time frame of a transition state. Good luck. And that's why it's hard, right? And so you pay this enormous penalty. I think they call them tariffs these days. Remember that hydrogen oxygen is 1,230 millivolts. So that represents between 1/4 and 1/3 of the energy content, which is an enormous loss. And so the idea, how do you mitigate that so that it doesn't cost as much, so to speak? So what do we look for? Now that we're all experts on this, right? So you want the onset to be as early as possible and reach mass transport as quickly as possible. That's all you need. And so from this dark blue, which is the platinum, palladium, cobalt, is the best. This palladium and carbon is the worst. That's all you need to know, right? And talking about electron microscopy, 2 modes of imaging, so-called ADF, or analog dark field, for elastically scattered electrons, where the intensity is proportional to Z, the atomic number, to the 1.7 power, right? And so here, heavier elements look a little brighter than less heavy elements. So here's a platinum iron image, and you can see brighter spots and less bright. If you then take the inelastically scattered electrons and put it through an electron spectrometer, you can do elemental mapping, identify each individual element in a composite. And so here's a typical one. So here's an ADF image. Here's a palladium map and an iron map, and the composite. You can see that this catalyst really has a palladium skin and a palladium iron core. If you don't know that, you don't know what your catalyst is like. And going back to in electrochemistry, the surface is everything, you're out of luck. And so being able to do that, we do it here almost, like, of course we do, but very few places can do that. And there's only one David, so. And then, you can have the typical shameless propaganda for covers of jacks, etc. A lot of the catalysis is predicated on volcano plots, which is typically a plot of some measure of activity versus some energy term or thermodynamic variable. Platinum absorbs oxygen too strongly. It's on the wrong side of that, right? So how could we modify that? One way is to, there we go, thanks. We have a periodic table. I was in a chemistry lecture room. We need to have so if we look at first order transition metals, okay, and this is called volcano plot because, surprise, surprise, it looks like a volcano. And things like platinum 3 cobalt or nickel or iron, when you do that, you have a compressive strain because cobalt is smaller than platinum. That compressive strain lowers the binding energy, and you basically climb up that wall. And so we have extra diffraction for platinum and carbon. platinum 3 cobalt, C400 means it's an alloy phase. If you look at the phase diagram, go to 700, you get an ordered phase. And how do you know that? Because these tiny little peaks show up, and they don't look like much, but they tell you the story that you now have an ordered phase. I should thank, my former colleague, or late colleague, Frank DiSalvo, who was the first one who really, exemplified this. I remember when working with this, that looks really interesting. If you provide the platinum, I'll provide the cobalt. And the other thing, as you go in from platinum to platinum cobalt, you see displacement to higher 2 theta because this is a smaller lattice parameter. And so here's the images. You can see the 3 platinum layers. Here is real life. Here is Disney. So you can see that the brighter spots for the platinum, the less bright spots for the cobalt. If you do a line scan across one of these particles, you can see that there's a platinum skin, 0.6 nanometers. I'm still calibrated in angstroms. That's basically 2 atoms. Right? So you have a core and a skin that's 2 atoms thick. That is really, precision engineering, if you will. If you take a single particle and you do a line scan, you see high, low, high, low, high, low, platinum, cobalt, it's ordered, right? No question. And then the real test here for the electrochemistry, here's platinum on carbon, the alloy phase, and the ordered phase. The ordered phase, much better. And you say, well, 70 millivolts is not very much. Remember that 59 millivolts in the Nernst equation is an order of magnitude. To be clear, a factor of 10, and 70 would be like a factor of 20. So don't tell me it's small, right? And so you can ask the question, so what's the effect of ordering, right? And here I use a rowing analogy for the head of the Charles, okay? So here's 2 boats. The woman got the email and read it. They were rowing in the same direction. The guys, they say, who cares about damn emails or messages? 2 are rowing to the left, 2 are rowing to the right. Everybody's rowing and nobody's moving. So what does annealing do? It goes from that to that, and now we can. So even small effects can add up to big consequences in this context. Now, moving from acidic to alkaline. So the issue with acidic fuel cells, which is the vast majority, is that it requires precious metals. And so we're talking about things like platinum and palladium. And if you think those are expensive, try iridium, which is horrifically expensive. And so using or going into alkaline media enables you the use of non-precious metals, things like iron, manganese, iron, cobalt, nickel, copper. Also notice for the true nerds that acidic media, is red and alkaline blue. So we keep, this color coding in this whole thing. The net reaction is the same in both cases. Hydrogen plus oxygen go into water. Notice also that in alkaline media, that means high pH, water is a reactant. And that would be an important concept in terms of mechanistically understanding how these things work. So here's a paper now a few years ago in collaboration with our colleagues at Wuhan University in China. And so this is a manganese cobalt spinel, synergistic interactions. So here the manganese activates the oxygen and the cobalt activates the water. How do we know that? That is synergistic because we can do X-ray absorption spectroscopy, and here the signal for the manganese and the cobalt change at exactly the same rate with potential. It's not proof that it's synergistic, but it sure as hell is a very close call to that. Here's the voltammetry. Now you're experts, so you can see the red is better than any of these 2. Displaced to higher potentials, the individual metal oxides really don't compare. It's interesting that when we do rotating these experiments, the platinum is better than the manganese cobalt spinel. And that's because in this case, you have an ocean of water. In a fuel cell, you have a very tight water budget. And so we can compare the performance of a fuel cell at 50, 60% or 50% relative humidity, and the spinel does much, much, much better. And we think it's because it's easier for that metal oxide to handle the water at that interface. And so we make these things. This is work of Chihao Lipra, the best person in making MEAs for alkaline media. You cannot see the stream because it's really, really very thin. So you deposit the catalyst, you make the MEA, which is what that is, put it on top of that, these serpentine pathways. This is graphite current collectors, put them in a fuel cell and test them. And so here we have the power characteristics. Here we have cell voltage, current density, and the power. And we can see that this guy peaks at around 1.2 watts per square centimeter, which is the highest of any non-precious metal oxygen reduction catalyst. Right? And it far exceeds DOE, the same projections and milestones. But then we wanted, so that's still, the anode where hydrogen gets oxidized was still precious. So we wanted to make a non-precious system. Nickel works very well, but it passivates very quickly. And with like everything else, when in doubt, throw some graphene, right? It's going to make it better, right? And so here we have nickel coated with a thin layer of graphene. And what that does is stabilizes that interface and it prevents oxidation. And so in this case, we could reach 210 milliwatts per square centimeter, which is not exactly something to write home about. But you can develop that into something that gives you a watt per square centimeter, and now we're talking. This is viable commercially. The issue now is to get this to have long enough lifetime or longevity. But in terms of performance, this is as good as it needs to be. And so we go then into electrolyzers. So here we reverse the reaction. So now we're making hydrogen and oxygen. The cell looks very different because now you're evolving gases. You want those suckers to come out as fast as possible, right? And so here you can see gas is really streaming out. And so we've done some testing with this, looking at the current density. This is 1,000 hours. That's a very long time. And we're now, Chihao here somewhere? How many hours now? 2,000? 2,000, okay. 15,000 is what you would like under the best conditions. But if you get to 5,000 or 6,000, you can engineer a significant fraction of the rest. So we now sort of within striking distance of not only having very active, but also very durable systems. And so here's going back in time, the earliest operando TEM measurements in collaboration with David Muller. We suffered through this. It would have been 2013, 2014 in that ballpark. Okay. And so here's, this is in collaboration with the folks from Protochips. These are based on silicon nitride windows at about 200 to 500 nanometers. Here's a chip. So here's the working electrode, which is carbon, so that it's essentially transparent and non-catalytic. And then platinum and counter and reference electrodes. I know platinum is not a reference electrode. You don't need to remind me, but we use it for a reason, okay? And so here's a voltammetric profile for just the carbon, which is featureless as it should be. And then you put platinum, you can see the voltammetric profile. That is typical of platinum electrodes. And that is emphasized here. So this is what a cyclic voltammogram of a polycrystalline platinum electrode should look like in acidic media. You have oxide formation, oxide reduction, hydrogen adsorption on different crystal planes. In the microscope, it looks like that with the beam on or off. Nobody's going to argue that that is not platinum, right? And so that gets you at least to the first stage to be able to do other experiments. And so here's one where we apply a potential of 0.5 volts, which is not very much. And you can see that not much is happening there. If you get a bit more enthusiastic at +1 volt, whoops. This really has a mind of its own. There we go. And you can see really things moving. meaning at those potentials, you have very severe corrosion. You have all of these things moving around. Even more so here. So these are 2 nanoparticles. And you can see them coalesce. Why is that important? Because coalescence is one of the most important mechanisms by which fuel cell catalysts degrade. And it's because if you take 2 small particles and you make one big one, you lose surface area. Back to the idea, it's everything is the surface. You lose surface area, you lose performance. And you can then actually look at those trajectories and actually come up with like Monte Carlo simulations, figuring out which trajectory gets you there. Hopefully you want to not go there. And so you can have at least some sense as to how to control these processes. And so then this takes us to a little bit more advanced. This is work of my then student and now colleague, Yao Yang, looking at copper deposition at different potentials. -minus 0.1, you see planar growth. Notice the scale here, and this is the electrode surface. If you go over here, island shapes, and then on the extreme right here, dendritic growth. Keep your eye on this guy who is clearly isolated. But when the growth hits it, it gets electrified and that grows. Now, a rhetorical question. What was the best measuring instrument ever invented? Don't overthink this. The ruler, exactly right. The ruler. So if you put a ruler here, right? Measure the displacement and put as a square root of time, it's linear to as many nines as you want, meaning it's a diffusion process, right? And the ruler never runs out of calibration, right? This is batteries charging and discharging. And so you can, depending on where the lithium is, you see lighter or darker. You see nucleation of different nanoparticles in the battery itself. And this is real. This is not Disney or any of this stuff. This is a real battery operating. And so now we move into batteries lithium sulfur. Why lithium sulfur? If we look at your typical batteries in terms of theoretical energy or actual 387, 200, that's probably what you have. I'm sure all of you have like 5 or 6 of these devices, right? Lithium sulfur, theoretical, 25,687. That's 8 times that. 500, 2.5 times that, right? Also, sulfur is essentially free. You know that the Egyptians had pyramids, the Aztecs had pyramids, the Canadians have pyramids. This is, I had to take that shot, but boss. These are pyramids in Canada. These are sulfur. Just to give you a sense of scale, keep your eyes here. You see that little dot? That's an SUV. Okay? So there's plenty of sulfur. It comes from desulfurizing oil. But if you want a mountain of sulfur in your backyard, somebody will pay you to take it. Okay? It's complex, electrochemistry. You can again see, the typical profile here. The first 2 electrons, remember that sulfur is an 8-membered ring. The first 2 electrons break that ring, and then you chew up and make so-called polysulfides. There's this thing called the shuttle, and you can see here the space shuttle, meaning that you can have connections between the anode and the cathode, and it gives rise to self-discharge, which is not good. And this looks deceivingly simple, but it's not. If we look, so this is what this is accelerating time, what the changes are from elemental sulfur to long-chain polysulfides to shorter polysulfides. And then we'll see at the end, we accelerate this. Let's just finish. That this will remain basically colored, okay? And you have to hand it to battery people. They will refer to this as capacity fade. That sounds like benign. It really tells you you're losing stuff, right? And you lose enough stuff in a few cycles, you're dead. The typical efficiency on a battery to be useful has to be 99.99%. Think about that. How many things do you know that operate that well? Not many. Right? If you lose 1% per cycle, you have 100 cycles. And typically, a battery is considered dead when you have 80% of the initial charge. So you get 20 cycles at 1% loss. So if you're 99% efficient, and most people would think that's terrific, not in this case. And you want to do at least a couple thousand cycles. In real practice, 10,000 cycles. You do the math, right? You can do diffraction. Again, call out to Chess and all of the great people there. These look like little popcorn. You see this thing coming in and out, and then eventually becoming featureless. And from that, you can come up with something like this that tells you the peaks coming in and out as a function of time. And in particular, you make lithium sulfide, which is the end product, before the full discharge of the battery. What does that mean? That there's a way to go from reactants to products without having everything converted, which means that you can go to faster charge discharge. Right? And then this is work of Sung-Ho Yu, who is somewhere in here. There we are. So this is microscopy and diffraction of lithium sulfur. This is also done at Chess. And so remember when I said that the first two electrons, you break that ring. So this is elemental sulfur. So the expectation is that when you come over here, all of that yellow will disappear. Right? And so if you look at that, boom. Right? And it's not accidental. That's what's supposed to happen. And then you can recharge. Right? And so if you look closely, there's a little bit of a hint there. And you can, then boom, it comes back on. After the first recharge, if you do it many times, they nucleate at the same place, meaning that there's something specific about those sites. It turns out to be, oxygen containing, and you would think it's a little bit more polar. These polysulfides are very polar. And so that then you have a way to generate an interface that is more reactive by controlling that surface chemistry. And then using confocal Raman, we're now getting sort of closer in time here, 2022. This is work by Xuanyang Lang, now a professor in Beijing in China. So here the assumption is in confocal Raman that the area is that you see the image is proportional to concentration, which is a reasonable assumption here. And so here you see, you can follow the conversion from elemental sulfur to the polysulfides. And so this plot has like 95 points. And I would call that a pretty good fit to first order kinetics, meaning it's a ferrokinetic process. Okay? And so then you can come up with at least a plausible mechanism for how these things charge and discharge. And that is you start with S8, SA2 minus, and then go this way, and you don't have to go through all the other intermediates. And that then provides a window to making battery performance that really works well. And then, of course, you have to make these things a little bit more practical. So here, what we did is make sulfur spheres. You can see the distribution here, and coat them with aniline. You can use ammonium persulfate, which is a very strong oxidizing agent. That would polymerize the aniline to make polyaniline. So it's polymeric shell. You put this in a little bit of toluene and extract just a little bit of the sulfur. Why do you want to do that? Because sulfur, when it discharges, expands. And if you try to expand that, you can figure out what's going to happen, right? Imagine you have an egg, you expand it, what's going to happen? That's what happens, right? They all break. But if you extract a little bit, they basically remain nice and pristine. This is 200 cycles. A call out to Conamics, and Steve Burkhardt is here. They're commercializing this technology, right by the airport. All of these batteries are predicated on a lithium metal anode because you have such a high capacity cathode. But dendrites are problematic because you give rise to catastrophic failure of your battery. And so, as I say, really don't try this at home. Right? This is sort of making dendrites, you know, on command. Right? Do you remember, you know, the early PCs that the back was like a cylinder? That's where the batteries were, right? And so the batteries are called 18650, which is 80 millimeters in diameter, 65 millimeters in like a little hot dog. If you take the equivalent size of dynamite, the battery has more energy. Okay, so keep that in mind, right? And so in order to understand this, we did X-ray imaging of lithium metal. Again, Professor Song-Ho Yu, who did all of this work. You can see the growth of the lithium. By controlling the conditions, you can see that is a dendrite growing in front of your face, right? This is a little bit more uniform, and that's because the concentration of electrolyte is 0.5 versus 0.1. The Debye length here is much shorter, right? Remember, it scales as 1 to the square root of the ionic strength. And so it's easier to do the deposition. And then you can develop electrolytes and you can see really nice and flat. And you get deposits that look like that. That's very flat of the thickness that you want. Now it's a question of how do you combine these two things to make sort of, you know, reliable devices, which is really what we'll want to do here. And then if you're lucky, and here's Professor, you get your name written in lithium. It's probably the most reactive name card ever made. And the scale here, 200 microns. And so, slight change of pace here. So for the next, I was told to keep it under 3 hours, but I think 2 hours would be. We got about 10 minutes left or something. So the so-called Abruña Energy Initiative, this came about the Odyssey Pre-Settlement Fund. Translation, when Volkswagen was caught lying like hell about emissions, right? There was this enormous lawsuit. I think it was like 15 billion or something. And when it was settled, there was a little bit of money left, little in that context. It was $32 million that had to be used for renewable energy projects. And so I wrote a proposal, you know, basically 30 seconds of history. Dean at the time, you know, sent me an email like a Tuesday night saying, this happened. I'm talking to the board of trustees tomorrow. I need a proposal by tomorrow morning. You're the boss, you have a proposal, right? And so I wrote this proposal that included both batteries and fuel cells, 8.6 million. And then the development office always gets in, want to split them to increase the chance of getting something. But sure. Fast forward, we actually got both. And so we got 8.6 million from the 32, which are available to the whole world. And so the dean said, because it was my crazy idea, it had to be called the Abruña something, and that's where the Abruña Energy Initiative came about. Couple of things. So the first level 3, and this really works, and here's our fearless leader charging his catalytic. It's interesting because here, capture the moment, we just cut the ribbon and it's still free floating. And then, of course, Vieques, which is where we were last week. Maria devastated Puerto Rico. That's faster than a Formula One car, just to put it in perspective. So what happens? Right? The hurricane was bigger than the island. Every time I see that, I get emotional because I know what that was like. And you get that, and that, and that, and that. There was no electricity produced for 18 months. We complain when the lights go off for 3 minutes. Oh, what the hell is wrong with it, right? 18 months. People depended on diesel generators, etc. And so clearly, it's a compelling need to remedy this. And so what we're trying to establish is a cycle where we use Renewables, mainly solar. Wind, it doesn't make much sense in hurricanes. And so you have renewable energy in solar panels, an electrolyzer, hydrogen cylinders that can be used in a fuel cell to generate electricity or transport. All of this at this place called La Finca de Humberto. This is Vieques. Vieques is an island east of Puerto Rico, about 8 miles out, population of 9,500. Just to give you a sense of geography. So here's the region, Dominican Republic, Puerto Rico, Vieques, and this little one here is called Culebra. We were there last week. So Paul and Daniel from Efforts Here and Alex, who developed this app. I mean, this is really interesting. This app that all you need is latitude and longitude. It'll give you the solar radiation, everything you need to develop a plan for renewable energies. We have QCR codes for that. We also have the user's manual in English, and I translate it into Spanish, so it should be pretty good too as well. And then Oscar Ruiz and Bestrade, who are in the Finca de Humberto, and I cannot make this stuff up. She is actually a Cornell grad. And that's Humberto. Humberto is a pig that on his hind legs is about 7 feet tall. So we're there last week. This is a 150 kilowatt hour battery that we shipped it there in the middle of hurricane season. I mean, it's magical that it got there. And then these folks here made it work with solar panels. Like 3 days before we got there, but they got it done. And so here's the little panel being charged. It charges in about 8 hours. It provides enough electricity to keep 3 refrigerated containers at frozen temperatures, because it's a farm and they keep, chickens and whatever else you want in there. And so we come here to the people responsible for all of it. It's your fault if your name is up there, right? 66 PhD students and about 85 postdocs. And the best thing that I will ever do in my life. And Hong's in particular special as somebody who's been with me for a very, very long time. Collaborators, many collaborators at Cornell, collaborators at other academic institutions, DOE, and external collaborators worldwide. These people really are the ones who make it happen. As I mentioned earlier, I might be the face, but they do the work, right? Through the years, this was the very first group picture. My first 2 students, Carlos Cabrera, Ana Guadalupe, my first postdoc, Prasanna Chandatsekar. And you can see evolution, and we're sort of somewhere in here in the last couple of years. For those of you who knew me in a previous life, we used to have this party. I would cook for my entire group and boyfriends and girlfriends and pet rocks. I would have like 40 people in my house, which was small. I would do all the cooking, right? It was the menu was the same. 5 pounds of shrimp, 5 pounds of calamari, 5 pounds of scallops, 30 pounds of pork, 4 pots of rice, 3 pots of rice and beans, and about 25 to 30 bottles of wine and some of not so well provenance. The first and last, first Carlos Cabrera, Mikhail Khromov, who is somewhere in here, is now a postdoc with Peidong Yan at Berkeley. Tells you something when you look like that and that stage and like that today. And so, let's see if we can get this. There we go.
We're solving the energy crisis.
Solving the energy crisis?
Trust me, I'm a professional.
You hear that? Trust me, I'm a professional, right? And especially, the people that, Hong Seng-Wan, probably the best in the world of DEMS. Chi Hao Li, the best in MEAs for alkaline media. They still remember when I turned 40, I was in 7th floor of Olin. I'm driving in and I hear this, Lordy, he's 40. And the inside, there was, I still have that a sheet that, at birth, and I have a beer at birth with a cup of espresso. And then when I turned 50, they put these red lights. This is Olin. Everybody got a cold from my lab because my birthday is in November. It was cold, but you have to admit that was pretty impressive. When I turned 60 in the new building, The dean called me, is it your birthday? What gave you that hint, right? And then after 20, 25, and 30 years here at Cornell, notice at 30, we have now a bicycle because Steve Burkhardt, who is back there or here, is responsible for my being in cycling. Like every normal, well, we'll get to that in a second. And so a couple of years ago, July 5th, I've been here 40 years. And so they made this banner, which is amazing. That's a real cyclic voltammogram. It has a little bit of noise here, you can see. You know, climbing, you know, it's like climbing buffalo. And a little cake with a number of, particular number, the first paper I ever published here, et cetera. And of course, like every normal person, I own 12 bikes, 7 in Ithaca, 3 in Puerto Rico, and 2 in Brazil. Again, there was this symposium a couple of years ago, which is humbling beyond belief. CABES, Center for Alkaline-Based Energy Solution, which is the DOE center that I direct, and Danielle and Paul, who are just saints, you know, period. They just make this happen day in and day out at CABES, as well as the AEI, the Abruña Energy Initiative. Bringing home the bacon, the pig, the bacon, and the Baker Lab, NSF, DOE, CABES, Dreyfus Foundation, Initiative, New York State. Here's from the initiative, thanks to Nel Hydrogen, Viridi, who provided the battery, and Enro, who provided a lot of guidance into how to get these things done. We do have a web page and the origami car, which looks kind of cute. SN2 reaction, I don't know if the organic chemists will need to tell me that. ECE or ECE disproportionation if you're an electrochemist. And on a side note, Frank Tisau, my best collaborator ever, Tom Rutledge and Mike Lanesky, who passed away just a few weeks ago. I'm sure God wanted to go fishing, so he called on Frank, and Michael, he wanted to go cycling and called on Tom. And then finally, my parents, Minerva and Fernando, both passed away. I hope they have a good internet connection to listen to this in heaven. My 2 brothers, Fernando, he's actually older than me. Yeah. Julio, Gustavo, Frank, and Otavio, who are, he's here, he's in Brazil. And of course, Celia. Yes, an amazing woman. And so I finish with, I often ask people, why do we do what we do? Right? So many things you could do. And so we do this because, as I say, deep down, we believe in the transformational power of science to improve the human condition, especially those in need, the vulnerable ones. And with that,